The period of July, August, and September was characterized by the accelerated tempo that always precedes an imminent launch. All over the country, planning, manufacturing, testing, and training moved ahead at a high speed. At Kennedy Space Center, the receipt and checkout of space vehicle components and hardware far exceeded the volume of any other comparable period. In Kennedy's Spacecraft Operations Building, 5 modules of Apollo spacecraft were inspected and tested during this quarter. In early July, the command and service modules for the Apollo 7 mission, the first manned flight of the Apollo program, underwent a successful series of unmanned altitude tests. Later in the month, the prime crew for the mission, astronauts Schirra, Isley, and Cunningham, took part in a manned altitude test, essential to the flight plan. In the first part of the test, which was conducted at a simulated altitude of 226,000 feet, the cabin atmosphere was pressurized at 60% oxygen and 40% nitrogen. Later, the cabin pressure was vented to simulate space conditions required during extravehicular activity. During this phase, the astronauts, relying solely on spacecraft systems for environmental support, performed many tasks designed to check out their ability to work in pressurized spacesuits. Near the end of the test, the command module atmosphere was repressurized to a 100% oxygen environment at 5 psi, the normal shirt-sleeve environment used in orbital flight. Following a repeat of the manned altitude test with the backup crew, Stafford, Young, and Cernan, the spacecraft for the first manned Apollo mission was declared ready for flight. It was hoisted from the altitude chamber and prepared for transport to the launch pad. On August 9th, the Apollo 7 command and service modules were moved to Complex 34 at Cape Kennedy and mated to the Saturn 1B launch vehicle. This first manned Apollo flight is scheduled for launch in October. The mission is intended to verify proper operation of the command and service module systems and the operational capabilities of the command service modules, the crew, and the manned spaceflight network support facilities. The low Earth orbit mission is scheduled to last up to 11 days. Following several pad tests of the mated Apollo 7 space vehicle, the launch crew and astronauts rehearsed emergency egress procedures at Complex 34. The slide wire is one mode of emergency egress from the White Room at the 220-foot level of the launch tower. A high-speed elevator to the base of the tower and the launch escape rocket are the other means. The slide wire concept was validated during this quarter. A number of mannequins ranging in weight from 170 to 225 pounds were used for functional tests of the concept. On August 30th, in a simulated emergency egress, 5 men rode down the wire at 10-second intervals. Astronaut Ron Evans, wearing a flight suit, took part in this test. No problems were encountered, and the slide wire was certified man-rated. A similar slide wire egress system is being developed and tested for the manned Saturn V series, which will be launched from Complex 39 of the Kennedy Space Center. In mid-September, the preparations to launch Apollo 7 reached another critical test, the countdown demonstration test of the first manned Apollo vehicle. In the interest of astronaut safety, the test was conducted in a 2-part series, which is now standard procedure for manned launches. In the wet portion of the test, all countdown activities up to engine ignition, including fueling of the Saturn stages, were conducted. The test ended at T-3 seconds. For the dry portion of the test, the fuel was first detanked from the Saturn vehicle and the countdown picked up at T-6 hours. Fueling was simulated during the dry test in which the astronaut crew participated. The 3 men entered the command module at the normal countdown time, or T-2 hours and 25 minutes, and proceeded to perform all spacecraft activity required prior to ignition. Later in the month, a flight readiness test, which included a tie-in with Mission Control in Houston and with the Manned Spaceflight Network, reviewed all of the major activities scheduled from engine ignition to completion of the planned 11-day mission. With the successful completion of this test, Apollo 7 was ready for its scheduled October launch. An accelerated pace was also evident during the quarter at Launch Complex 39 in preparation for Apollo Saturn V manned missions. The second stage for Apollo 8 had passed cryogenic testing at the Mississippi Test Facility in June, and upon its return to Complex 39 was re-erected atop the Saturn 503 booster. Apollo 8, the first manned flight using the full Saturn V propulsion system, is presently defined as an Earth orbital mission to further evaluate command and service module performance and procedures. However, final objectives will not be completely established until after analysis of the Apollo 7 flight. Following re-erection of the third stage and instrument unit, a facility verification spacecraft was mated to the Saturn 503 launch vehicle to enable continued pre-launch testing prior to the mating of the flight spacecraft. The lunar module, originally scheduled to fly on Apollo 8, was assigned to the follow-on Apollo 9 mission in a major rescheduling announced during the period. A lunar test article will be substituted for the lunar module on the Apollo 8 mission planned for this winter. The command as well as the service module for the Apollo 8 mission was tested in one of the two altitude chambers. By the end of September, the spacecraft and the launch vehicle for the first Saturn V manned mission were ready for mating. Meanwhile, the lunar module for the second manned Apollo Saturn V mission, Apollo 9, was placed in the second altitude chamber where unmanned and manned tests were conducted during September. The second and third stages for this mission were undergoing checkout in the low bay test cells of the vehicle assembly building. During the unmanned Saturn V flight, Apollo 6, which occurred last quarter, several technical problems developed. The solutions to these problems required intensive engineering activity during this quarter. The two major problems were the excessive vertical oscillations, or pogo effect, that occurred during the first stage flight, and separation of several pieces of material from the lunar module adapter area, which was apparently caused by the severe oscillations. After extensive data reduction and study by NASA and contractor personnel, one of several possible solutions for the pogo problem was selected. The solution consists of adding helium to an existing cavity in the liquid oxygen pre-valves of the first stage propulsion system. This forms a shock absorber, which changes the natural vibrations of the propulsion system to about 2 cycles per second. Comprehensive static firings of a single F-1 engine were conducted both at the Marshall Center and the Edwards Flight Research Center, California, to obtain data to verify the validity of this solution. Engineering analysis of test data revealed that the fix was completely effective. In early August, a final and full-scale test of the pogo solution was conducted at the Mississippi Test Facility. The first stage for the 6th Saturn V vehicle was fitted with accumulators and fired for full duration. The analysis of data from the firing indicated that the pogo problem is solved. The oscillation levels for the upcoming Apollo 8 flight will not exceed those of the first unmanned Saturn V, which made a perfect flight last November. The fix has already been applied to the first stage for Apollo 8, the first manned Saturn V mission. All other Saturn V first stages are currently being modified. Even though the solution of the pogo problem is expected to also solve lunar module adapter material separation during flight, further studies into this latter problem were conducted at both NASA and contractor facilities. Meanwhile, at the Manned Spacecraft Center, vibration tests of the entire Apollo spacecraft, the instrument unit, and the third stage adapter section were conducted. One of the important results of these tests was the decision to replace the hinged panels of the lunar adapter section with panels that will be jettisoned in Earth orbit. In other tests of Apollo Saturn V components, the second stage for the third manned Saturn V mission was successfully test-fired at the Mississippi Test Facility in August. At the Marshall Space Flight Center, final testing of a lighter Saturn V second stage was nearing completion. The objective of the lightweight stage is to increase the payload of the Saturn V vehicle by reducing its gross weight. The anticipated gain in payload will be over 3,000 pounds and will be first flown on the second manned Saturn V mission. And continuing water egress training in the Gulf of Mexico included the first manned Apollo prime and backup crews. The exercise consisted of placing the Apollo egress training spacecraft upside down with the suited crew inside. The crew then activated the uprighting bags to bring the spacecraft to an upright, stable position for egress. After going through a post-landing checklist, the crew climbed out into a three-man life raft to await pickup. In this training exercise, a new type rescue net was used to hoist the crew from water to helicopter. Still other astronauts at Perrin Air Force Base, Texas, underwent training in various forms of ejection, water impact, and water survival. Here, astronaut Russell Schweikert, using a takeoff technique borrowed from a mallard duck, becomes airborne to test his chute-release mechanism and flotation gear. Also during the quarter, development of Apollo applications hardware continued satisfactorily. Increased effort was expended in the area of subsystems testing. Development of the Apollo telescope mount continued on schedule. The Apollo telescope mount is designed to perform a variety of solar observation experiments from Earth orbit. In these preliminary investigations conducted in a KC-135 aircraft and under zero-G conditions, astronauts removed and replaced film cassettes at the lunar module end of the Apollo telescope mount simulator. Development tests are underway at Marshall on a portion of the Apollo telescope mount pointing system. This is the fine sun sensor system which will detect and remain pointed at the center of the sun, providing a reference base for aiming experiment packages. Here, the unit is undergoing checkout and preparation for further testing to determine accuracy and to obtain engineering data. Early in the report period, McDonnell Douglas completed 5 articles of Saturn I Workshop zero-G test hardware. These were shipped to the Marshall Space Flight Center for further development of test procedures. The articles included a section of the forward dome, a section of the common bulkhead, the waste management compartment, and a section of the crew quarters. The units were later shipped to Wright-Patterson Air Force Base for zero-G testing in a KC-135 aircraft. A subtle piece of space detective work was concluded this quarter through the combined forces of the Manned Spacecraft Center and the Jet Propulsion Laboratory. An unexpected shift in tracking data had been observed during the lunar orbiter flights. These phenomena raised serious questions about lunar navigation and landing accuracies. After intensive studies of orbiter data, it was concluded that large, high-density masses are present beneath the surface of the Moon. These mass concentrations, or mascons, occur only in the major ring mareas. They have now been pinpointed, and their effect on an approaching or orbiting spacecraft is now understood. With this information included in the spacecraft computer system, lunar navigation, rendezvous, landing, and takeoff from the lunar surface can be programmed with greater confidence. In summation, the third quarter of 1968 was marked by an increasing rate of vigorous and intensive testing, preparing the way for an accelerated early schedule of resuming manned flight operations after 2 years, leading toward the Apollo lunar landing mission.